Hemp plastics and composites, structure, processing, properties, and applications. Hemp-based plastics and composites have emerged as promising sustainable alternatives to conventional petroleum-derived polymers. Derived primarily from the bast fibers and cellulose-rich stalks of cannabis sativa, these materials combine renewable resources with tunable mechanical and functional properties. This report presents a concise scientific overview of hemp plastics, including their composition, processing techniques, structure-property relationships, advantages and limitations, and industrial applications. Particular emphasis is placed on recent developments in hemp fiber-reinforced composites, biodegradable polymer systems, and their growing adoption across automotive, construction, packaging, and textile sectors. Despite current challenges related to cost, scalability, and end-of-life infrastructure, hemp-based materials offer significant potential for reducing environmental impact and advancing circular material economies. The increasing environmental burden associated with petroleum-based plastics has intensified the search for renewable, biodegradable alternatives. Among various bio-based feedstocks, hemp, cannabis sativa, has gained considerable attention due to its rapid growth, high biomass yield, and exceptional cellulose content, typically 65 to 75%. These characteristics make hemp an attractive precursor for producing bioplastics and reinforcing fibers for composite materials. Hemp plastics encompass a broad class of materials, including fully bio-based polymers derived from hemp cellulose and hybrid composites where hemp fibers are incorporated into biodegradable or conventional polymer matrices. These materials aim to combine sustainability with high-performance characteristics, addressing both ecological and engineering demands. Composition and material design. Hemp plastics are primarily derived from cellulose extracted from hemp stalks. This cellulose can be chemically modified or processed into biopolymers such as regenerated cellulose, e.g., rayon or cellophane derivatives. However, fully hemp-derived plastics remain relatively rare. Most commercial systems are composites combining hemp fibers with other bio-based or synthetic polymers. Common polymer matrices used in hemp composites include polylactic acid, PLA, polyhydroxyalkanoates, PHAs, such as poly,3-hydroxybutyrate CO3-hydroxyvalerate, PHBV, and petroleum-derived polymers like polypropylene, PP, and high-density polyethylene, HDPE. In such systems, hemp fibers act as reinforcing agents, improving stiffness, strength, and thermal stability. The interfacial compatibility between hydrophilic hemp fibers and hydrophobic polymer matrices is a critical factor influencing composite performance. Surface treatments, such as alkali, sodium hydroxide, treatment, are frequently employed to remove lignin and hemicellulose, increase surface roughness, and enhance fiber matrix adhesion. Compatibilizers such as malleated polymers, e.g., malleated PBAT, are also used to improve dispersion and interfacial bonding. Processing techniques. Hemp plastics and composites are typically manufactured using conventional polymer processing techniques, facilitating industrial scalability. The most common methods include melt extrusion and injection molding. In melt processing, hemp fibers are blended with thermoplastic matrices under controlled temperature and shear conditions. Reactive extrusion may be employed when compatibilizers or functional additives are incorporated during processing. Injection molding is widely used to fabricate complex shapes, particularly in automotive and consumer applications. Recent studies have demonstrated the effectiveness of hybrid composites, such as hemp sisal fiber blends in polylactic acid matrices, which exhibit enhanced mechanical properties compared to neat polymers. Similarly, hemp fiber-reinforced HDPE composites incorporating both virgin and recycled polymers have shown improved tensile strength and stiffness when treated fibers are used. Biodegradable systems based on PHBV reinforced with high hemp content, up to 68%, have also been developed. These materials often include secondary polymers such as polybutylene adipate coterephthalate, PBAT, to improve toughness, along with compatibilizers to ensure uniform phase distribution. Mechanical and functional properties. Hemp fiber-reinforced composites exhibit a favorable combination of mechanical performance and lightweight characteristics. Compared to conventional plastics such as polypropylene, hemp composites can demonstrate significantly higher stiffness and strength. In some formulations, stiffness improvements of up to 5-fold and strength increases of approximately 2.5 times have been reported. The high aspect ratio and intrinsic strength of hemp fibers contribute to efficient stress transfer within the composite. Additionally, hemp fibers provide excellent vibration damping properties, making them suitable for dynamic applications such as automotive components and sports equipment. Thermally, hemp composites exhibit good dimensional stability and moderate resistance to heat and ultraviolet radiation. Unlike glass fibers, hemp fibers are less abrasive, reducing wear on processing equipment and extending mold life. Biodegradable hemp plastics offer another key advantage. Under appropriate composting conditions, certain formulations can degrade within a few months, in contrast to conventional plastics that persist for decades or longer. However, the degradation rate is highly dependent on the polymer matrix and environmental conditions. Environmental sustainability. Hemp plastics present significant environmental benefits across their life cycle. Hemp cultivation requires relatively low inputs of water, pesticides, and herbicides, and the crop grows rapidly with high biomass yield. Notably, hemp exhibits strong carbon sequestration (CSAMATA), absorbing substantial amounts of carbon dioxide during growth. The biodegradability of hemp-based materials further reduces their environmental footprint, particularly in single-use applications such as packaging. Additionally, hemp fibers are non-toxic and free from harmful additives such as pH phthalates and bisphenol A, enhancing their safety for human use. However, sustainability assessments must consider the entire system. Blends containing non-biodegradable polymers may only partially degrade, and industrial composting infrastructure is often required to achieve efficient biodegradation. Recycling of multi-component biocomposites also remains a technical challenge. Applications of hemp plastics and composites. Automotive industry. The automotive sector represents one of the most significant adopters of hemp composites. Hemp fibers are used to reinforce interior components such as door panels, dashboards, insulation mats, and trunk liners. These materials reduce vehicle weight, improve fuel efficiency, and enhance sustainability. Hemp composites have demonstrated superior specific energy absorption compared to other natural fibers such as jute and flax, making them suitable for impact-resistant applications. Their excellent vibration damping properties also enable their use in brake pads and acoustic insulation. Modern vehicles increasingly incorporate hemp-based materials as partial replacements for glass fiber composites. These bio-based components offer comparable mechanical performance while being lighter and more environmentally friendly. Construction materials. Hemp-based materials have a long history in construction, with modern innovations such as hempcrete gaining prominence. Hempcrete is produced by combining hemp herds with lime-based binders and water, resulting in a lightweight, insulating material with excellent hygrothermal properties. Hemp composites are also used in insulation panels, fiberboards, roofing materials, and structural composites. Their ability to regulate moisture and temperature contributes to energy-efficient building design. Additionally, hemp-based construction materials can sequester carbon, further enhancing their environmental benefits. Packaging and consumer products. Hemp plastics are increasingly used in sustainable packaging applications, including biodegradable bottles, containers, trays, and films. These materials provide an eco-friendly alternative to single-use plastics, addressing global concerns over plastic waste. In consumer goods, hemp composites are utilized in furniture, electronic casings, toys, and household items. Their durability, non-toxicity, and aesthetic appeal make them suitable for a wide range of products. Additive manufacturing. Hemp-derived filaments are gaining attention in additive manufacturing, 3D printing. These filaments, often produced from hemp processing waste, offer favorable mechanical properties, including improved strength-to-weight ratios compared to conventional PLA filaments. They also provide a sustainable route for valorizing agricultural residues. Textile and specialty applications. Hemp fibers have been used in textiles for millennia and continue to play a role in modern composite systems. Their high tensile strength, durability, and resistance to moisture make them suitable for fabrics, ropes, and technical textiles. In advanced applications, hemp fibers are being explored for use in sports equipment and musical instruments due to their superior vibration damping characteristics compared to synthetic fibers. Limitations and challenges. Despite their advantages, hemp plastics face several challenges that limit widespread adoption. One of the primary barriers is cost. Hemp-based materials are generally more expensive than conventional plastics due to limited economies of scale, supply chain constraints, and processing complexities. Material performance can also be a limitation. While hemp fibers enhance stiffness and strength, achieving adequate toughness and flexibility often requires blending with other polymers or additives. These modifications can complicate recycling and reduce overall biodegradability. Environmental degradation of hemp plastics is not always straightforward. Many biodegradable systems require industrial composting conditions, which are not universally available. Additionally, exposure to moisture and heat can affect the shelf life and stability of certain formulations. Regulatory and social factors also play a role. Misconceptions surrounding hemp cultivation and legal restrictions in some regions can hinder its industrial utilization. Future outlook. Advances in materials science, processing technologies, and agricultural practices are expected to enhance the feasibility of hemp plastics. Research efforts are focused on improving fiber matrix compatibility, developing fully bio-based and recyclable systems, and optimizing processing methods for large-scale production. The integration of hemp into circular economy frameworks represents a promising pathway towards sustainable material systems. By utilizing renewable feedstocks, reducing carbon emissions, and enabling biodegradability, hemp plastics align with global sustainability goals. In conclusion, hemp plastics and composites represent a versatile and sustainable class of materials with significant potential to replace conventional plastics in a wide range of applications. Their high cellulose content, favorable mechanical properties, biodegradability, and low environmental impact make them attractive for industries seeking greener alternatives. While challenges related to cost, processing, and infrastructure remain, ongoing research and industrial investment are driving rapid progress in this field. As technological and economic barriers are addressed, hemp-based materials are poised to play an increasingly important role in the transition towards sustainable and circular material economies.